My name is Aldhytha Karina Sari from UNSW, and this is my video submission for the final assessment item of the Mathematical Engineering of Deep Learning course at the AMSI Summer School. The paper that we selected is a 2018 paper from Google AI team on a new neural machine translation model called the RNMT Plus model. A little bit of introduction. In recent years, there has been a few research that uses deep learning techniques, such as neural networks, to construct a model that is able to translate a text from one language to another. This field is commonly known as the neural machine translation, or NMT. One of the models proposed is the RNMT Plus model. In this video, we will go through a computational experiment based on section 4 and 5 of the paper, where we implemented a simpler version of the RNMT Plus model and analyzed its performance in translating English to French and French to English sentences. We will also dissect some techniques involved in this RNMT Plus model, such as layer normalization, label smoothing, and multi-headed attention. In more details, we will see how the data is pre-processed into training, validation, and testing sets. Overview the model architecture. Train and test 8 neural networks constructed from the model, though we will only go through one of them. And analyze the result of our experiment. We begin by downloading and processing our data, which is a compilation of English and corresponding French sentences from this GitHub repository. First, we split each sentence into a list of words. We added an end-of-sentence token to the end of each sentence so that when we decode the result from the networks, we can trim it by the end of the sentence token to get the predicted sentence. Then, we tokenize the data by converting each unique word into a positive integer. We also add zero padding to the data to make sure they are of the same length so it's easy to train and test. We then separate the first 70% for training, the next 15% for validation, and the last 50% for testing. We also create the labels by converting the tokens into one hot encoding. Next, we will look at the model class we created using Keras. The RNMT Plus model follows the encoder-decoder model. In our model, we use 6 bidirectional layers for the encoder and 7 forward layers for the decoder, all of them using long short-term memory recurrent neural networks. This is how the model works. We take our embedded input data through a dropout layer into the encoder, where we concatenate the result of the forward and backward layers of the current bidirectional layer to be used in the next bidirectional layer. We add a dropout and layer normalization before the output is used as an input for the next iteration. Then, we project the result through the multi-headed self-attention into the decoder, where similar to the encoder, we concatenate the result of the current forward layer into the next forward layer. We also add a dropout and layer normalization before the output is used as an input for the next iteration. Finally, we concatenate the result of the decoder and the attention as the final output. Now that we know the model, we move on to training and testing the networks. First, we instantiate the model. If we want the model without multi-headed attention, we change the width attention parameter to false. The same thing applies for layer normalization. We compile the model using the categorical cross-entropy loss function with label smoothing of 0.1. If we want to run the model without label smoothing, we can remove the label smoothing parameter or set it to 0. The Atom optimizer is chosen with exponential decay learning rate. Then, we train the model by feeding in the training and validation data. We use 100 epochs with early stopping when the model has reached convergence and save the weights of the best model to disk. Here's the plot of the training and validation accuracy and loss. From looking at the loss trend, it seems to follow an exponential distribution and the accuracy goes above 90%. It takes approximately 1.5 hours for each model to be trained until convergence using the current hyperparameters. Now that we have our trained networks, we can test it. We load the best trained weights into the model and test it. The result is then processed by choosing the index of the higher probability in each column as the resulting token, and converting the tokens back to a list of words using our dictionary. Finally, we compute the BLUE score, a metric that is widely used since the early 21st century to measure the quality of a machine translation model. We calculate the score for each sentence using the NLTK library. The mean BLUE score for this model is 0.92 with standard deviation of 0.14. To see the quality of the translation in person, let's take a look at the actual translation versus the predicted translation. It looks perfect. After training and testing the other 7 networks, we have the following result. The English to French translation model performs better than the French to English translation model. The RNMT Plus model without multi-headed attention performs best at 0.9484, followed very closely by the RNMT Plus base model at 0.9472. The RNMT Plus model without label smoothing and layer normalization performs worst at 0.4465. From the table, we can conclude that the following is the order of importance, from high to low, of the techniques involved in creating an effective and good quality RNMT Plus model: layer normalization, label smoothing, and multi-headed attention. So that is the overview of the computational experiment part of this project. I hope you enjoy it, and thank you for watching.